Okay, hello everybody. We continue our lectures. So let's call today's section 11.1 theorems about Limbsoup and limit superior, limit inferior. I would like to recall definitions, so recall. Mainly I'll talk about Limbsoup because everything about lim_inf is analogous, so I'll start with Limbsoup. So there are two definitions. One is, in fact, it explains why such a notation is used. So the limit superior is the limit of such a sequence, supremum of all xk's with k greater or equal than n. That is one definition. And second definition is the limit superior of xn is equal to supremum Lxi, where Lxi is the set of all partial limits of the sequence xn. So these are two definitions, and both numbers are defined certainly for arbitrary bounded sequence, because if a sequence xn is bounded, then this is not empty according to Bolzano-Weierstrass. And as we checked during the last lecture, the sequence, let me denote it by Bn supremum, and this sequence Bn is decreasing. So Bn is decreasing. That was proved during the last lecture. So the first theorem today is that both definitions are equivalent. Both definitions of the limit superior are equivalent. Moreover, the limit superior is a partial limit So, proof. Here I'll start firstly with, consider bounded sequences. So it means that we have xn is bounded, right? And then, as we mentioned before, both definitions give some bounded numbers as their values. So in fact, what we have to prove that both numbers are equal. So if just for a moment those are two different numbers, both are defined, very well defined, and now we want to prove that they coincide. So denote L is the limit superior, let's say according to the first definition, so limit of supremums of the sets so we take members of our sequence for indices k greater or equal than n, we consider supremums, and we take the limit of this sequence L. So now we want to prove that L is simultaneously is the supremum of the set of all partial limits. That is what we want to prove. So if we want to prove that something is the least upper bound of a certain set, then we have to prove two assertions. The first one is, so the first assertion says that L is an upper bound. So first claim is that L is an upper bound for the set of all partial limits. So by contradiction, so what means by contradiction here? Suppose L isn't an upper bound for Lxi. So what means that a number is not an upper bound of a set? Then there exists some element L in our set Lxi such that L is greater than capital L. So we have a greater number, So what means L belongs to the set of partial limits? L is a partial limit. So L is a partial limit of our sequence. Hence, so we may write is limit j tends to infinity x and j. X and j. Okay, now put epsilon equals to L is greater than capital L, so L minus L over 2, and that is a positive number by our supposition. So then from the definition of the limit, what can we deduce? By definition, we can find a natural number capital J such that for all j greater than capital J, we have x and j minus L less than epsilon. And in particular, what we have that x and j is greater than L minus epsilon, and L minus epsilon is, if we substitute, L minus capital L over 2, and that is L plus L over 2. So, what it means, so for arbitrary, now let us consider the sequence. Consider the sequence Bn now, right? So, what we deduce then? Look, for arbitrary natural ends, there exists j greater than capital J such that nj is greater or equal than n. Why? Because nj is strictly increasing sequence of the natural numbers, hence it will be larger than arbitrary given natural number n for a certain index j. And of course, if we choose j is larger, then the inequality is still valid, hence we may suppose j is greater than capital J. But then what it means? If j is greater than j, so maybe, okay, I will indicate it just here. So from this inequality, that j is greater than capital J, we have x and j is greater than L plus L over 2, right? And nj greater or equal than n. And recall that Bn is supremum for all xk such that xk greater or equal than n. Hence, Bn is greater than L plus L over 2. Because Bn is supremum. Now, what we have? For arbitrary n, Bn is greater than L plus L over 2. Then by properties of the limit, that was theorem about a limit of inequalities and limits. So if we have this inequality, then the limit of Bn is greater or equal than L plus L over 2. So we can take a limit in inequality. And this limit is nothing else but capital L, because that is Bn. So capital L is this one. And look at this. That's impossible, because capital L is smaller than small l, so L plus L over 2 is greater than L. And that means that we have a contradiction. Now there is a question, what does partial limit means? Partial limits is just this one, so the limit of a subsequence. So we don't consider all indices, but just only part of natural numbers, increasing sequence of natural numbers and j, and take a limit of that sequence x and j. So it means that the first claim is proved. First claim is proved. So now, how to finish the proof of the theorem for this case of for bounded sequence. Look, we want to prove that capital L is the least upper bound. Now we know that L is an upper bound. So to finish the proof, it's sufficient to prove that capital L is indeed a partial limit, because what it means? L belongs to this set and it is an upper bound, hence L is maximum, because we cannot find a larger number than L, which is an upper bound. So now it means that we need to prove the second claim, and in fact it finishes the proof for bounded sequences. L is a partial limit. Okay, look, so it means we want to construct a sequence x, let it be m k, such that the limit of x m k is equal to capital L. So look at the definition of capital L. That is a limit of a sequence, so I'll write the definition. So L is limit of the sequence of Bn. So by definition, what it means, for arbitrary epsilon greater than 0, there exists number n natural such that for all n greater than capital N, we have inequality Bn minus L less than epsilon. Bn is decreasing, so in fact we have that Bn is decreasing, so Bn is less than L plus epsilon. In fact, it is greater or equal than L, since Bn is decreasing. And in fact, we don't need it essentially, as you will see, because look, now what we want to use. So Bn is supremum, so let me write it in details. That is supremum all xk such that xk greater or equal than n. So I wrote the definition of Bn. So we have the least upper bound of a certain set is in those limits. And yeah, so in fact what is important is that it is greater than L minus epsilon. Now let us choose, let's say, epsilon equals to 1. Put epsilon equals to 1. So there exists certain capital N such that for all n small greater we have this inequality. And if the least upper bound of certain set is greater than L minus 1 now, right? Then there exists an element from this set, let us call it, there exists xm1 such that it satisfies same inequality with epsilon equals to 1. So once again, we take epsilon equals to 1. We know that the least upper bound is between L minus epsilon, L plus epsilon. The set here is, okay, k greater or equal than n is arbitrarily greater than capital N, or we may fix some number, doesn't matter which number now. And we can choose one index. So, to explain theorems, axioms, and so on, after that you write them down completely once again for better understanding. Okay, of course, I'm not going to write down, for example, all theorems like here, right? So, there was theorem if we have every member of a sequence greater or equal than fixed number, then same inequality is valid for the limit. And that is just, I repeat it fast. Now, look, what I used here, that was definition, precisely, just definition, nothing else. Here is written. No more, nothing more. So, in fact, up to now I didn't use anything except for the definition. Okay, maybe for the definition of supremum. Supremum is the least upper bound. So we have the least upper bound is in this, between those numbers, L minus 1 and L plus 1. The least upper bound of a set. Then there exists at least one element of our set which is also in the same limits. Because otherwise we could take L minus epsilon as an upper bound. So I took this element as xm1. That's it. Yeah? Then, look, take epsilon equals to 2, right? Oh, sorry, 1/2. 1/2. 1/2. Then there exists another number, capital N, such that for all indices n greater than capital N, and I want now n greater than m1. So look here, yeah. I want to take n greater than m1. Why? Because now for this n I have same inequality with epsilon equals to 1/2. And if I have such an inequality for the least upper bound of certain set, then there exists an element of our set which is also in the same limits. And so I'll write there exists x m2. Okay, maybe I'll write here m2 greater than m1. Why it is greater than m1? Because I choose n greater than m1, such that same inequality holds now with 1/2. And I can continue. I continue it. So epsilon take 1 over, let's say, j. I consider small n greater than mj. Then there exists mj plus 1 greater than mj, such that L minus 1 over maybe here j plus 1 less than x mj plus 1 less than L plus 1 over j plus 1, and so on. So it means that we construct an increasing sequence of integers, strictly increasing, in fact, strictly increasing, strictly. So we have construct a strictly increasing sequence of natural numbers such that, for all natural j, we have L minus 1 over j less x mj less L plus 1 over j. And then we have two policemen theorem. J tends to infinity. The sequence in the left hand side and the sequence in the right hand side have the same limit, capital L, hence the sequence in the middle has the same limit. the whole proof. The whole proof of what? The whole proof. Oh. The whole proof of axioms. Axioms are assertions without proof, right? And but if you want that I should repeat the whole proof of all theorems which I used here, that's too much. Sorry. Yeah, here two policemen theorem, right? Which says that if we have such a double inequality, the left hand side and the right hand side have the same limit as, let's say, j tends to infinity, then the middle tends to the same limit as well. What I write on the board. Okay, here I wrote the definition of the limit. Here I wrote the definition of the limit again, nothing else. That is a property of strictly increasing sequence of natural numbers. If we have strictly increasing sequence of natural numbers, then it is unbounded, hence you can find a number which is greater than arbitrary given number. Nothing else. And then here, property of the limits for sequences. If you have member of sequence greater or equal than another, so theorem which I used here, if an less or equal bn for all n natural, and limit an equals to a capital, limit of bn equals to capital B, then a less or equal than b. That's it. Okay, and here I used only the definition of the supremum, which says this is the least upper bound. It means that any number which is smaller, for example that one, is not an upper bound. What means this is not an upper bound? Hence there exists an element of this set which is greater. That was used here. Nothing else, nothing else. Okay. Two policemen theorem is practically written. So, yeah, so we constructed a subsequence which has the limit capital L. Second claim is proved. Hence, the case of bounded sequences is considered completely. Right? Okay. Now let's continue Now I'll erase it. So I hope that I explained everything what was written on the blackboard. Now just definitions, property of increasing sequence of natural numbers, that theorem, again definition, and here definition of the least upper bound, nothing else. Yeah, two policemen theorem, that's all. Okay, so now what remains for the proof? So bounded sequences were considered. What else? Then, what is about unbounded sequences? Now, in fact, the proof which was given works for sequences bounded above. Nothing else was used, if you will look carefully, because if the sequence is bounded above, then again this exists, and also that set of partial limits is bounded above, and we don't care about boundedness below here for the limit superior. So now if xn is unbounded above, then what happens? What happens? Unbounded above. In fact, it was mentioned at the end of the last lecture, so then what it means? Then supremum of such a set is plus infinity for arbitrary n. Hence, okay, then it means that it is natural to accept the upper limit superior is also plus infinity, right? Because every member of that sequence now is plus infinity, hence it's natural to take it as plus infinity. And then again Lxi contains plus infinity. Why? Because what means unbounded above? Look, xn is unbounded above. Is unbounded above. So it means that once we try to find an upper bound, we fail. So take arbitrary, let's say, M natural, there exists N, and I'll cite that xn greater than m. That is just from unboundedness. Okay, let's have a break. Let's continue. So now, look, that is written the definition of unboundedness. So it means once we try to find a candidate for an upper bound, it is not an upper bound, so it means there is something which is greater than this upper bound. Now, look, we may construct a sequence. Which sequence? So let's say just take m equals to 1. Then there exists n, and I'll write it n1 such that x n1 greater than 1, right? Then take m is maximum of 2 and x1 and 1. Then, for sure, we can find, oh, in fact, here, why I wrote here m is natural, not natural, just real. Unbounded above, no upper bound, no real upper bound. So maximum of 2 and x and 1, that is again a real number. Then there exists an index, I'll write it n2, natural, such that x and 2 greater than 2, because greater than 2, and also n2 is greater than 1. Okay, I should write here, sorry, I should write here maximum x1, so on up to x and 1. So all indices up to n1, I should count here, right? Then n2 is certainly greater than n1 because it cannot be among those. Okay, then we can choose m equals to maximum of 3 x 1, so on, x and 2, and then there exists n3 such that x and 3 greater than 3 because of this, and n3 greater than n2 since all indices smaller are not suitable, right? Yes, then what it means? It means we can continue, so on. So we have nk natural. Yeah, okay, if we choose maximum of k, x1, so on, up to x and k minus 1, and x and k greater than k, and simultaneously nk greater than nk minus 1. So it means we have constructed a sequence of natural numbers increasing. Hence we have subsequence x and k of our sequence xn, and x and k greater than k for all natural k. Then it follows k tends to plus infinity as k tends to plus infinity, hence x and k tends to plus infinity as well. Yeah. And it means that we constructed a sequence, subsequence, which has the limit plus infinity, hence plus infinity belongs to our set. And that's all for our theorem, even for the last case of unbounded above. So the proof is finished. Okay. Now there is one more possibility to characterize limit superior and limit inferior. Yeah, of course, let me write down. I'll not give it proof, theorem 1 prime. Both definitions of the limit inferior coincide. Moreover, limit inferior is a partial limit. So the proof is completely analogous, or one can prove just by the following observation. So the limit inferior by any definition is equal to minus limit superior of minus xn. Why? Because if you put here minus, then supremum becomes minus infimum of, so let's say supremum of minus xk, where k greater or equal than m, is equal to minus infimum of xk, like that, such that k greater or equal than m. That property was mentioned when we considered supremums and infimums. Or just there is a nice word, analogously. Here indeed you can proceed completely analogously. Okay, now what is more essential? Theorem 2. Let xn be a bounded sequence. L equals to limit superior of xn if and only if two assertions are satisfied. First, for arbitrary epsilon greater than 0, there exists natural n such that for all n greater than n, xn smaller than L plus epsilon. And second, for arbitrary epsilon greater than 0, for arbitrary n natural, there exists n greater than capital N such that L minus epsilon less than xn. So you see that the first part is a part of the definition of the limit, in fact. The second differs by quantifiers. Two quantifiers are different. So, proof. So, proof of theorem 2. Proof of theorem 2. We can use any of those definitions, or even in parts, doesn't matter. Okay, let me use the second one. So L is supremum of the set of partial limits, right? Then, look, let's prove the first one. Proof first assertion, right? So what we want to prove is written here, and maybe it's easy for me to use another definition. It doesn't matter. By contradiction. By contradiction. Contradiction. By contradiction. So we suppose an opposite. It means there exists epsilon greater than 0, such that for all natural n, there exists n greater than n, such that xn greater or equal than L plus epsilon. Let me write here epsilon naught to make it clear that epsilon is fixed. Epsilon naught is fixed. Right? Now look, again, here it is written arbitrary capital N, so I can use, let's say, n, just take 1, so then what exists I'll call n1, such that xn1 greater or equal than L plus epsilon naught. Then I'll take n equals to, let's say, n1. So then there exists a number n which I'll denote by n2 greater than n1, such that xn2 is still greater or equal than L plus epsilon naught. And so on. We continue up to infinity, right? So then we construct a subsequence x and k, k from 1 to infinity, such that for all k natural, we have x and k greater or equal than L plus epsilon naught. That is a bounded sequence because the whole sequence was supposed to be bounded. So by Bolzano-Weierstrass theorem, there exists a subsequence of that sequence. So subsequence of subsequence, subsequence. There exists subsequence, so x, n, k, l, l from 1 to infinity. So it means now we consider not every k, but some sequence of natural numbers k, l, l from 1 to infinity, right? Such that that sequence has a limit. L tends to infinity, x n k L, it has a limit. And what can we say about that limit? Since every member of that sequence greater or equal than capital L plus epsilon naught, same inequality holds for the limit. And that's impossible, because what we have here, this is subsequence of our sequence, so that is a partial limit, and it cannot be greater or equal than L plus epsilon naught. So it's a contradiction. The first is proved. The first is proved. And now proof second. Proof second again by contradiction. Now what is by contradiction? There exists epsilon naught positive such that there exists capital N natural such that for all n greater than capital N we have opposite inequality. It means x n, okay, let me write like it was written, L minus epsilon greater or equal than epsilon naught xn. And what it means? Look, so we have, there is a number capital N such that all members of our sequence less or equal than L minus epsilon. Now it means take arbitrary subsequence which has a limit x and k belongs to the set of partial limits, of course, right? Then what we have? For sufficiently large k, so there exists capital K, such that for all k greater than this capital K, and k greater than capital N, which was chosen. Hence, x and k less or equal than L minus epsilon naught. Then we can take a limit. So the limit x and k is less or equal than L minus epsilon naught. So look what it means. We have proved that arbitrary partial limit is less or equal than L minus epsilon naught. So L minus epsilon naught is an upper bound for the set of all limits, partial limits, for the set of all partial limits. So, and that is a contradiction, because we supposed capital L is the least upper bound, and we have smaller upper bound. That is contradiction. So it means what we have proved? We have proved that our conditions are necessary. Now we'll prove, so it means we have proved part, this part. This part is proved. It's here, right? Now we prove the opposite assertion. opposite assertion. So it means we suppose both 1 and 2 are satisfied. 1 and 2 are satisfied. 1, 2 are satisfied. We want to prove that indeed this number L, which is mentioned, is the limit superior. The limit superior. Okay. Look, what follows from the first equality? So it means that if we take arbitrary subsequence, for arbitrary subsequence, which has a limit as k tends to infinity x and k, so this is a partial limit, this is a partial limit. Then again, like at the end of the proof, for arbitrary epsilon, we take arbitrary epsilon, fix it, and then we have, there exists k natural such that for all k greater than capital K, and k will be greater than this capital M. Look, so nk is greater than capital N. So it means I can put here, and just this nk for arbitrary k greater than capital K. And it means that we have x and k smaller than L plus epsilon. For arbitrary k greater than k. Then, by the properties of limit, the limit of x and k is less or equal than L plus epsilon again, right? Now look what we have proved. We have proved that for arbitrary epsilon greater than 0, partial limits are less or equal than L plus epsilon. It means that we have that arbitrary partial limit is less or equal than capital L. Less or equal than capital L. Hence, L is an upper bound for the set of all partial limits. So, once again, what we did. We take L, the number from those two, right? Assertions, we suppose they are satisfied. Then we consider arbitrary convergent subsequence. So here we take arbitrary element of the set of partial limits. Then by the properties of increasing sequences of natural numbers, we have this. So we take in one n as that nk. So we have inequality x and k less than L plus epsilon for all k greater than capital K. Hence, by properties of limits, limit of x and k less or equal L plus epsilon. And this inequality now is proved for arbitrary epsilon greater than 0. And if we have such an inequality for arbitrary epsilon greater than 0, then we have that inequality as well. And so now for arbitrary partial limit we have the inequality which says L is an upper bound for Lxi. That's it, right? That follows from 1. Now for 2, okay, we may observe once again, I may repeat same construction, so once again what 2 gives. Look, we have epsilon equals to firstly, let's say 1, right? Then, okay, we may choose n1 such that L minus 1 less than x n1, right? Okay, then we put epsilon equals to 1/2. Then for arbitrary capital N we have something. Now I'll take n equals to n1. So there exists n greater than capital N, and n equals to in fact n2 now, right? N2 is by definition this n. Such that L minus 1/2 less than x n2. And we continue. So epsilon 1/k, capital N is nk minus 1. There exists n greater than capital N, and in fact it will be nk now L minus 1/k less than x nk. So now we have constructed subsequence x and k, k from 1 to infinity, such that for all natural k we have inequality L minus 1/k less than x and k. X and k is bounded sequence, so there is a subsequence x and k L, convergent subsequence. The limit as L tends to infinity, x and k L, there exists that limit, and what we have for that limit? Look now. We have for arbitrary L, L minus 1/k L less than x and k L, because here we consider some subsequence, so also natural numbers. This inequality is valid. And then, now we know the limit exists, so the limit will be greater or equal than the limit of the left-hand side, and the left-hand side is L, right? And as we proved, arbitrary subsequence, convergent subsequence, has a limit less or equal than L. So, from the first part, first part, I mean that one, we have the limit is equal to and what it means, L is the least upper bound, and the proof is over, right? That's it. Okay. Of course, similarly, let me formulate theorem 2 prime theorem 2 prime. 2 prime. So let xn be a bounded sequence. Then L is limit inferior of xn if and only if the following is true. First, for arbitrary epsilon greater than 0, there exists n natural such that for all n greater than n, L minus epsilon less xn less, okay, nothing else. And second, for arbitrary epsilon greater than 0, for arbitrary natural n, there exists n greater such that xn smaller than L plus epsilon. Again, proof is analogous, and there is quite important theorem which is a direct corollary of theorems 2 and 2 prime. So xn is convergent if and only if limit inferior and limit superior coincide and finite. Proof. So, if xn is convergent, then it is bounded, as we know, is bounded. There was an assertion about it. So we may use both theorem 2 and theorem 2 prime, and then theorem 2 prime first part, theorem 2 first part and theorem 2 prime first part also. What they imply, let me write down. For arbitrary epsilon greater than 0, there exists n natural. In fact, of course, what I should do more precisely. Okay, here I should take n1, there n2, and then that one is maximum of n1 and n2. Such that for all n greater than n, we have simultaneously those two inequalities, and those two inequalities together mean xn minus L in modulus less than epsilon. And that is precisely the limit equals to L. And in fact, the converse is also similar. Yeah, so it's sorry. It's similar. So if we have both limits coincide, then we take same number L in both assertions. Altogether, they mean that one, right? And that is, yeah, so once again, it follows from those two follows that one, right? So once again, if we have limit superior and limit inferior coincide, then we can take them here, capital L, we can take in both 1 and 2, and we deduce what we want, right? Okay. And then small example. So example, find the limit superior and limit inferior for those sequences 1/2, 1/2, 1/4, 3/4, 1/8, 7/8, and so on, 1/2 power n, 2 power n minus 1/2 power n, and so on. Here it is easy to find two convergent subsequences, so a to n is, so with even numbers, it will be 2 to the power n minus 1/2 to the power n. A to n minus 1 is 1/2 power n. So we have two convergent subsequences, and the set of partial limits, here, LAI, contains two elements, 0 and 1. This partial limit is 0 here, and partial limit is 1. Hence, maximal element is the superior limit, which is 1, and limit inferior is the minimal element, which is 0. That's it. That's it. Okay, so it seems now I gave everything. Yeah. Okay. That's all for today.